Hello, my name is Jay Metz, and welcome everyone to the Storage Networking Industry Association's second webinar in a series on storage performance benchmarking. We're a part of the Ethernet Storage Forum, a group devoted to the promotion and education of all things storage. This webinar is going to build upon the first in the series, which laid out the foundations of metrics and terminology for performance benchmarking. If you haven't seen that webinar yet, don't worry, we'll provide a link to that as well. Here, though, we're going to be looking at the bigger picture, examining the more holistic question of solutions under test. And additional webinars will explore aspects of storage performance in the future. A little bit of housekeeping before we begin. This webinar in its entirety will be provided afterwards in both PDF and PowerPoint formats. And all parts of this webcast series will be posted to the SNIA Ethernet Storage Forum website, as well as available on demand. Additionally, we will collate all questions and answers from this webcast into a blog article. This webinar is, of course, free, but please note that this material is copyrighted by SNIA, and that any slides used by member companies must be reproduced in their entirety without modification, and SNIA must be acknowledged as the source. So, just who are the men behind the pumpkins? Well, today we've got Ken Cantrell, Manager of Performance Engineering from NetApp. Over the years, he's worked on both SAN and NAS performance analysis, and he was lobotomized and became a manager about 8 years ago, but remains active in engineering efforts, including representing NetApp within SPEC and SNIA. We also have Ken's partner in crime, Mark Rogov, a systems engineer at EMC. Mark's career spans 20 years, the last 11 of which has been at EMC. He joined as a NAS subject matter expert, a calling that he still answers to. And finally, there's me. I am your host and moderator. My name is Jay Metz. I'm a research and development engineer for Cisco, and I'm going to be taking your questions and relaying them to Mark and Ken. Other than that, I'm simply here to model the hat. Finally, you can follow us on Twitter at SNIAESF, at RogovMark, at Ken Cantrell Jr., and at Dr. J. Metz, some of the more plain and descriptive ordinary names you'll find on Twitter. So now that my first official duties of Master of Ceremonies is complete, let's get to the meat of the presentation. So over to you, Ken and Mark.
Thanks, Jay. So just so you know, voices, this is Ken Cantrell.
And this is Mark Rogov.
So before we get started really into today's presentation, we're going to take a really quick detour. Last time, through the Q&A, we got a bunch of questions about SPEC because we mentioned that both Mark and I are active members of SPEC and more specifically the SPEC SFS subcommittee. So we're here partly on behalf of SPEC as well as on behalf of SNIA. And we got questions about, well, what is SPEC? So very, very briefly, SPEC is the Standard Performance Evaluation Corporation, and SPEC is a vendor-neutral industry body that creates, in large part, benchmarks. So there's a graphics benchmark, a CPU benchmark. Mark and I both work on SFS, a solution file server benchmark, which Mark is
which is also known as a NAS, or a file benchmark. We talked about NAS and file in the first webcast, but even though it's called SFS, think of it primarily as a NAS way of benchmarking.
And the big thing about SFS 2014 is that we like a lot is it's a very business-oriented benchmark. There are 4 very distinct workloads: software build, VDI, VDA, and database. VDA stands for Video Data Acquisition. VDI stands for Virtual Desktop Infrastructure. So if you have more questions about SPEC SFS, feel free to contact either one of us directly. If you want to know if your company is a member of SPEC, you're welcome to contact me directly.
And with that, we're going to move on. Our entire webcast series was thought originally as an introduction to benchmarking. When we sat down and we planned it out, we thought, well, there's many things that we would like to talk about. And what we really did is laid out 5 different big versions of it. And on July 30th, we did talk the first time about metrics and terminology, some of the simple stuff and the foundations necessary to enter the field. And today we'll cover something called solutions under test. We're planning to do several more in the future, and the plan currently is to talk about the block components, talk about the file components, and finally, as Ken likes to call it, the coup de grace, the winner of them all, the crown jewel of it all is workload definitions. Now, at the end of this presentation, we would like you guys to do the rating for how the session was done. And we also would like to survey and see if there's anything else or other components or session and topics that you'd like to talk with, for us to talk. And we'll definitely take that into consideration. The topics we have on the board are not set in stone. We're live people. And if there's interest in something particular that fits the entire calling, we'd gladly do it. But today's session, we'll break it out in several chapters. And we will start today based on introduction, followed by solution and a test, followed by some caching discussions, and then we'll have some of what we're trying to do, 3 different examples. We're going to talk about those examples. Right now they're known as a mold here in MidiBytes per second, but we'll talk more about that, and then finally we'll wrap it up. So without further ado, let's jump straight into the introduction and review a little bit the webcast that we had last time.
Right, and I'm going to go ahead and I'm just going to interrupt you, because for anybody who wants that little guide about where we are, we've jammed it down in the corner, so you can always see where we are as we move through the presentation as well.
So clearly right now is introduction.
Yes, indeed.
All right, so last time we did the webcast on terminology, and I put a little bit here graphics from the terminology that we had last time. We came up with these leaves, and each leaf would define a term. It was just a visual way for us to present terminology, so as you remember. But the majority of the presentation was really spent in section we called Graph Fun, where we talked about 2 different systems. And also underlying this entire thing was that the bridge that was connecting perhaps a non-technical approach to benchmarking and connecting the real application runtimes, we said use benchmarks. Benchmarks are your friends, and as an example of a benchmark is spec, which we talked about earlier. However, I don't want to concentrate more on the first webcast other than the fact that last time...
Right, so a lot of what we focused on last time, right, we made 2 charts, like you would see here, and we asked the question, which one of these is better? If you've got 2 storage systems, 2 storage solutions, they're both being asked to do the same work, which one of those performance charts is better? Which one of them would you want to buy? And I think that this is really, we got some pretty good feedback from the last presentation, and I think this is really the part that connected with people pretty well. So if you haven't seen it, I would definitely look at the last 30 minutes of the last one, because it was a lot of fun to do. And we were really pushing that idea.
And we were going back and forth. The whole point was we're trying to say, hey, it depends, which is a favorite phrase. But what it depends really on is it would depend on business context. And that was the bottom line of the first webcast, that context makes metrics matter. And the metrics that you could be examining systems could be anything.
Right. So we looked at response time. We looked at MidiBytes per second, and IOPS, and we've even looked at some strange metrics, dollar per rack unit, for example. And the big point was, depending on what you care about, one of those is better than the other, of those 2 charts that we showed. And what we're going to do today is, we're going to ask a different question. So instead of asking which one is better, we want to start asking the question, why would they be different? So if you have 2 different storage solutions, they're both being asked to do the same work, why would one of them be faster or slower than the other?
Or in essence, we wanted to say which component of what you're trying to test matters the most.
Right. And I think so if we're going to short circuit to the end a little bit, we're going to kind of paint a picture that says you're going to get different performance because some part of those 2 different storage solutions is different from the other. And which one of those components is going to matter the most? We can't answer this question fully today. So don't expect, 35 minutes from now, 40 minutes from now, that you're going to have the perfect answer to this. That answer will continue through future broadcasts, but we want to give you the idea and start that question.
And that brings the end of the first introduction section. So this is a point where we will break for a little bit and go back to Jay and see if there's any pertinent questions we have that we need to address before moving on.
Not yet. You haven't screwed up enough yet.
Excellent. I like that. So let's move on straight into the solution under test.
Let me stop you. Okay. So we did a few dry runs, and when we've done dry runs, people have said very, very quickly, why are you calling this a solution under test and not a system under test? So let me break in and try to answer that question.
Well, one of the reasons why we call it solution under test and not system under test is if you look historically at what's happening and you look at the slide right now on the screen, you realize that we start with simple stuff. So if we look at the laptop and say, hey, Ken, can I run a benchmark on a laptop?
Yeah, absolutely.
And if it's a laptop, then it's a system. But if I start growing what I run my benchmark on, it could be a server. It could be a hypervisor where I can have one VM sending some I.O. because it's running the benchmark client, and the other VM receiving the I.O. because it's running some benchmark server, for example. That is still the same thing, but now it's no longer a system. It is closely a solution. It becomes more evident as we increase the complexity when we say, well, what if my storage solution has a storage array? And I have my hypervisor on a big server going over some fiber channel lines to a storage array where my storage sits. And then ultimately all the way on the right, where we may have some hosts that are running Linux or operating systems or even hypervisors, connect over with the network to a storage solution, which in its own turn on the back has some connectivity that goes to the drives.
So we're calling it a solution under test because it's more than just the dedicated storage array necessarily that's affecting performance.
That's right. So that's the key point, is when you run performance benchmarking, it is not just the storage array that's participating in what's happening. It's also what's going on in your client. Something that we have seen time and time again is when the clients go in there, enable their own local cache, all of a sudden the numbers are different.
They're different, but let's not jump ahead because we'll get to more on that. But we got to go back. Let's go back for just a second, if we can.
We can.
So part of what we want to point out here a little bit is that over on the left-hand side with the laptop, all of the components that make up your benchmark or your storage solution over on the laptop are really the same components that are all the way over on the right-hand side of this line of complexity, right? You still have people who are asking to do I.O. You still have your I.O. having to go somewhere. On the laptop, it's a hard drive. On the right-hand side, maybe it's a whole bunch of disks behind a storage controller. So we're trying to paint a picture that we have all of the same components, but you can package them differently. Is that fair?
That's very fair.
Okay.
But we're going to look at it, though. We're going to look at the system on the right, the painted in green in here. We're going to put it on its side, and we're going to examine the entire solution and test. Whoops, wrong slide. We're going to examine the entire solution and the test in layers. And the layers in this case, we're going to have the layers that the clients have. We're going to have a layer of the front-end connect. We're going to have a layer that we're going to call storage controller, the back-end connect, and then the physical storage.
So in this picture, you generally will have I.O. moving, which is not maybe the way people would think, but our I.O. is going to move from the right-hand side, being generated by clients. It'll move through the connect, over into the storage controller, through the back end, and off to finally to the disks on the left-hand side.
Unless it's a read I.O., which will generate on the left and go to the right.
Well, but the I.O. request would still be coming from the clients on the right. So pretty much everything's beginning over on the right and moving to the left.
That's right. So the other thing is to mention that the solution of the test is going to include cables. It's going to include protocols and switches. It is a big, big bucket that we are putting things together, even in layers.
So this is interesting then. So part of what we're saying here is that these are the logical split here then of the same stuff we were showing on the first slide. We could package all this together in a laptop. We could split it off into a bunch of different components. But part of what you're telling me is that if I change something on my client, then I've changed my solution under test. One of the reasons I might get two different benchmark results is because I changed something on my client.
Bingo.
Not necessarily something on my
So something ubiquitous like you install a new patch on your Windows client machine that has changed some firmware somewhere within the client, and now the networking port is acting differently. And if you're running a NAS benchmark where networking port is important, that may have a very big effect on what you're getting out of your solution under test. Which means that if you run a benchmark yesterday, you went home, an update happened, you came back and you run it again today and you got two different results, The reason for those two different results could very well be this little patch that was installed, in this case, in the Windows operating system.
Interesting. So, and just to reiterate this one more time, the solution under test involves all of those components, hardware and software, that are part of the I/O process from beginning to end, whether that's your client all the way down to your disk.
But at the same time, change is not necessarily bad as long as you realize what has changed. Right, we get these phone calls every now and then on our escalation processes, and that, hey, nothing changed, I get a different number. Well, there could be something that changed you didn't realize.
Okay.
So when the I/O is sent from the client to the storage controller, and we look at it as a front-end I/O, which it sometimes may look different from one test to the other.
Okay, so this picture is happening in part because you just used that word front-end and back-end. We use these terms in our first webcast. Got a bunch of questions in Q&A afterwards. What is a front-end? What is a back-end? And so I think, it's worth explaining those terms, right?
So let me take a stab at that, Ken. What you see here in the picture is we painted our solution under test in two different colors, and we split the storage controller in half. And if we look at the storage controller, everything to the right of it, we see some I/O. The 2 MidiBytes I/Os are coming in from the host to the storage controller. The storage controller takes that incoming I/O, and to the storage controller, what's happening on that side is the front end. It's the I/O that it is receiving.
So you're just making up a 2K I/O as an example. We're not saying all clients always do 2K I/Os.
No, just an example.
Okay.
But the point we're trying to make is that when the storage controller analyzes that I/O and does what it does with it, the storage controller may decide to package it differently and send back to the physical storage in 8K I/O sizes, just because it thinks that happens to be a better solution. It could be a configurational option that somebody took with that storage controller.
Okay, so restating that, you have 2K I/Os coming in. If the storage controller knows it could do I/O more efficiently to the disks, your storage controller might coalesce all those 2K I/Os and then do 8K I/Os out to the back end. And so the reason we talk about front end and back end is because we've got two different kinds of I/O patterns often. Something happening from the clients to the storage controller, and then something the storage controller is doing back to its disks, and they often look different.
They often look different. And sometimes, a lot of times, front-end and back-end I/Os don't align or equate to each other because of some other architectural differences.
Okay.
On the back-end, fewer things like RAID groups and things of that nature.
So I'm going to save us time in a minute because I'm watching the questions as they come in. And there's a question about whether or not a storage controller is a compute node. So in the picture that we're drawing here, I think we would say more that the clients and the hosts might be your compute nodes. They're the people who are asking somebody to do work, and that there's a controller somewhere that's controlling where do IOs live on physical storage. That's doing some level of mapping. If you're on a laptop, your storage controller is the OS itself. If you're in a more complex environment, then your storage controller is your system vendor. So maybe an EMC box or a NetApp box is what we would be calling that storage controller in the middle.
That's right. And interestingly, we have a question because when we look at these IOs coming in, they technically represent something we call the workload. So let me ask you a question, Ken. Is a workload a part of solution under test?
No. Easy answer, no. Workloads run on the solution under test. And you did the same thing I did. You called it a system under test. It's really hard to call them a solution under test.
Did I? I said solution.
Maybe. We'll see.
But if we say system, by the way, the audience, we mean to say solution. We are also updating our own vocabulary in our heads. It is a solution under test because it's a very, very complicated set of layers that goes into the solution.
Okay. So workloads, whether that's a benchmark or an application, they run on a solution under test.
All right, Neil, we're going to pause for a second and look at questions again. Jay, how are we doing?
Not too bad. We got a couple of them. Your concept of storage controllers has generated a couple of questions. So, for example, one of the questions that comes in is when you're talking about storage controllers, question number one is you're talking about effectively a compute node, right? And then for the second one, for hyperconverged systems, a storage controller and compute nodes are the same. So I think that you might want to clarify what you refer to in terms of controllers versus.
So I think I answered the compute node one a second ago when I broke in. whether or not in a hyper-converged system, and that was part of what we were trying to do with that first picture, was show lots of different variations. Yes, in a hyper-converged system, your storage controller and your compute nodes would be packaged together in the same physical box. They would be logically distinct, which is why we're going to continue to show the picture we are with the different columns, but they are physically in the same node.
And then secondly, the question also came up as to are the performance numbers that vendors typically publish, are they front end or back end?
They are front end. So the numbers that most people will publish will be what does a client observe when they are accessing the storage system, which would make it a front end number.
Excellent.
All right, moving on into a section called cache. So we're going to begin to answer the question that we said in the beginning, is which component matters the most, or which element in this picture affects performance. And we would like to talk a little bit about the fact that when we look at these elements, they consist of pretty complicated different things as well. All right, if we look at the clients, we say, hey, the client has a CPU, it has memory, it has some caching in it, it has the OS, it has the patches. But what's interesting is, does it relate anyhow to other layers, Ken?
Well, and actually, I mean, the question that you're answering there as you list all those out is, which part of my client and my host could affect performance, right? And you basically just said all of it.
Yeah, I did. I did, yes.
Whether or not it was file system, the layout, or CPU, or memory, whatever. You just basically said everything on my client can affect performance.
That's
and I
correct.
would say the same thing is true back on the physical storage. So from a physical storage perspective, we're skipping the storage controller for a minute. All of that matters. So whether you have a 5200 RPM drive or a 7200 or a 15K drive, they all affect performance. If they have different firmware on those drives, so that this is an interesting one that we've both seen in our labs, you can get exactly the same vendor, exactly the same model, and if they have different firmware, you can get different performance results. The big one would be the drive technology, right? I mentioned RPMs, but the difference between SSDs and physical drives, spinning rust, right? Huge performance difference.
That is a big performance difference. And the other thing about the firmware is kind of interesting is what we're trying to say, and this actually we have seen this, is that when one drive goes bad and you replace it with another drive, we have changed the solution under test, especially if that other drive has a different firmware on it. So you may have different performance numbers out of that system solution.
And then what elements in the SUT affect performance? There's also the storage controller. I will say that there are aspects to the storage controller that absolutely matter, right? So we've got memory and CPUs and all sorts of parameters and configurations of how you could adjust the software on your storage controller. All of that matters.
And also things like number of pipes, the speed, the distance, and the protocol that the clients are connecting with. But let's take a look and see what's really common between them all. And when we look at it and we said, you know what, the common theme that we've said so far is that there is something processing, like a CPU or an ASIC, and then there is memory and cache. And they seem to span all of these layers, which is kind of interesting.
It is. I mean, we even have memory in our drives, right? So pretty much all drives that you buy are going to have memory that's used as a read cache. If they're consumer drives and you're using them at home, you might even have a write cache. That's pretty much turned off on all enterprise drives, but they might even have a write cache on them. That's a place to hold writes temporarily before they're flushed out to final storage. There are other things in common, right, other than just CPU and the processing elements in the cache. But part of what happened is Mark and I started asking the question, why would two different solutions under test be different? And we started listing out all the components, and we realized that every one of these columns had memory in it and had cache in it, and it's
kind of interesting. When we were preparing for this presentation, Ken shared that he has a very famous favorite interview question when he would interview people for a job in performance engineering for storage specifically and ask them to...
Yeah. So I draw this picture. I draw a physical storage and some clouds on either side, a storage controller in the middle, clients on the other end, and I ask the question, where does cache exist in this picture?
So it's interesting because I would like to answer that question as if I'm trying to apply to work for Ken. And this is what I'd be drawing on the whiteboard, is we will have those 5 different layers, and I will have the I/O on the right, which is generated by the client operating system. And the first cache that the I/O is going to encounter on its way to the physical storage is going to be the cache right there on the client. And that cache could be very simple. It could be big, it could be small, it's still there. And the I/O lives in that cache for a little while of its life, and then is moved on to the front-end connect, which could be some network somewhere. And it could be hitting some switch, and that switch may have some buffering, which effectively is very close to cache. And for the lack of this presentation, we'll just bundle them all together and not go into the differences. But after it lives a little bit in that cache, it moves forward and hits the storage controller. The storage controller has cache, and we know about that, and we kind of expect it, but the I/O will then transfer further and move on into the backend connect. Well, the backend connect cache existence could be could be there, could be not, depending a little bit what's going on. It could be, if it's a SAS or a SCSI controller, it may not necessarily have any buffering in there or cache, but if it's a cloud interconnect, let's say we're storing the data actually on the cloud, we will then go through some cache, and finally, we're going to hit the cache on the physical storage. Now, assuming, again, this is an enterprise solution, it's not going to be write cache. It could be read cache, at which point the I/O is going to sit in there on the way back, but nonetheless, there exists to be a cache. So as a very general answer to Ken's general question, a cache exists everywhere.
Cache exists everywhere, and it's more complicated. It's such a fun question, because if I ask this, people can give me 3 or 4 different caches on a client. They can give me 3 or 4 caches on the storage. I mean, you can go super deep. Some people go super shallow because the deepest they go is like the cache in Internet Explorer, which is pretty funny. But you can give all sorts of caches. And that's the big point, is that why are 2 storage solutions giving you different results? Lots of times it's because they put cache in different places, and they're caching more aggressively in one place than another. And we'll walk through some examples of what that means in a minute. But recognize that where you put memory into a storage solution and what you do with it has a huge difference on how they perform.
And on that note, it's kind of interesting because by how we place the cache or where we place the cache, we're inherently using one of these 3 principles that I would like to use throughout this entire presentation. There's a principle for...
Well, so what we're about to do, we're about to move into a mode here where we're going to show you some examples of how could you improve performance on various storage solutions. And we're going to do that 3 different ways. The first one is doing work faster. So if I ask my kids to go and clean their room, one way they could clean their room faster is simply to work faster. They're going to do the same amount of work, they're just going to do it faster. So we'll work through an example of doing work faster.
And if I ask my kids to clean the room, they're going to be done a lot faster because they just won't pick up as many things.
So the second principle of how you can get their improved performance is do less work.
That's right.
And then the third
one, if we're going to put both of our kids, sets of our kids together in the same room and ask them to clean, effectively they'll clean the room faster because there's going to be simply more of them.
Right. So they might do the same level of work. They all might individually work the same speed, but because there's more of them doing it, then they can do work faster.
Because that's going to increase the parallelism.
And so part of what we want to do is show you some different ways of setting up a storage solution and how these principles could change performance. And as we get into that, this will be a good place to stop and ask for questions, Jay.
I actually would like to skip this time because we're a little bit behind on our times.
He's got lots of questions.
And then, okay, well, let's do that, but we're a little behind, guys.
Okay, so I'll try to make it really easy, but as expected, your cache conversation generated a lot of questions. And we are unfortunately going to have to, we're going to have to skip over some of the questions happening. But when you refer to front-end caching, can you give an example of front-end, and are you referring to cache from fiber channel or network switches, or specifically on the storage arrays?
So front-end cache would be everything from that line drawing the middle over to the right, which could be cache at the storage controller. It could be cache at the client in terms of a file system cache or an operating systems cache. It could even be like the L1, L2, L3 caches. In the front-end connect, it's harder because you would tend to think more of buffering, but just think of memory in your network switches.
Or you could think about it that if your front-end interconnect is really long, like the internet, there's some sort of a relay that you're hitting. There could be an easier concept of cache there as well.
And just to let people know on the webinar that we will be posting all of the answers to the questions in a subsequent blog. So if we don't get it to you, don't get to it on the air, we will cover them in a subsequent blog.
All right, so let me move on into the first example section, something that we call a game of whack-a-mole.
So, Mark, what is my picture here? What are we trying to show in this picture?
All right, so this is a picture where we came up and we said, hey, do you remember in the first webinar we talked about the aggregate of the response time, how the response time gets to be a sum of all response time of the layers we pass through?
Right. So we said that first time, if I'm doing an I/O from my client all the way back to my physical storage, that the response time or the latency observed by my client would be adding up all the response times along the path.
So what we have done here is we've set up a separate time for each layer that has a response time. So you have a client, they have some sort of response time in there. Each interconnect has a response time. The storage controller has response time, and then the physical storage has a response time. So if you imagine an I/O going from the right to the left, and the latency for that I/O is going to be a sum of all of these individual I/Os that we've depicted in this graph.
Couple of clarifications that people have asked when we dry run this. We're making an assumption that every I/O in this example from the client will go all the way to physical storage. Okay. In the real world, that might not happen, but for the purpose of the example, assume that every I/O is going from the client all the way to physical storage. Number two, the numbers that we have for backend connect, storage controller, front-end connect, and clients are made up. The number we have for physical storage is going to be an average. We'll talk about that, a real number. The rest of them are made up numbers.
This is a theoretical example to understand and display the principle, not to be used as a reference as this is what the normal latency for this particular layer is. But when we look at this latency, so now when we set the table, we see that, hey, my physical storage latency is 1,000 times larger than its neighbor.
So if I'm looking at this, my latency is clearly dominated by my physical storage. If I want to know why it's taking 12 milliseconds, it's because 11 of it is my physical storage.
And we call this condition disk bound, or sometimes we'll refer to it and say this is a disk bottleneck. And
I'm going to note here that for people who've been doing this a very long time, using the word bottleneck here, or even saying disk bound, could be strange. We'll show you later how most people tend to use that word. It actually works as a definition. We went and looked it up. But basically what we're saying here is that because this component is the one dominating your perception of performance, you're never going to get faster than that performance in terms of latency of that disk drive. So it is your bottleneck. And
so when we get a bottleneck like this, so let's think about what we can do with it. So this is a normal environment. Imagine we have a normal solution under test. We look at the performance numbers. We don't like them. We examine the latency of every single layer, and we find out that this one particular latency of the physical storage is horrendous because it's a 7,200 RPM spinning drive. Anything we can do with that, Ken?
I think we can. We could start to apply that first principle. Let's make it faster.
All right. Well, what can we make it faster with?
So we can make it faster with SSDs. You know, one way we could do it is just use an SSD instead. Now, Mark, this is a pretty compelling chart about why SSDs are a good thing. Can you explain what we see here?
Well, I'm trying to, because I see this ridiculous tower on the right and almost nothing on the left and in the middle. Is there any way we can redraw this chart so we actually feel the difference?
Well, I was going to say we feel pretty good here, but we can show this. So part of what we want you to notice here is the huge difference here in response times for SSDs, which would be the 0.1 milliseconds versus an HDD. What we did is we did a survey across a whole bunch of different SSDs, a whole bunch of HDDs. These are the average response times for a random write, based on some industry surveys we did.
And then we also have the DRAM in there in nanoseconds, and this entire chart on the left is all nanoseconds. So to kind of emphasize, I think, you see how 11 milliseconds is so much bigger than the next thing? we decided to redraw this and use a logarithmic scale so we can actually have a little bit of a sense of what things are and show you the order of magnitude.
So we're looking at 2 orders of magnitude faster hard drives compared to SSDs.
That's right.
Why SSDs are so...
So we're suggesting that in our example that we have said previously, when we have a really slow drive, we should replace that drive with an SSD. All right, and if we do that, the interesting thing happens. The response time on the physical storage goes down to 0.1 milliseconds. And that makes all the other response times all of a sudden more visible because my entire baseline on the left, my entire dimension goes from 12 milliseconds to 0.7 milliseconds.
Right. So part of what's happened here is nothing to the right of physical storage has changed. Those numbers are exactly the numbers we showed on the previous chart. But because the SSD provides such an improvement in response time, when we adjust the scale on the left, all of the others appear to have changed and they all pop up and they look bigger. But we've not actually changed any of them.
Okay, and then just for the sake of an argument, now we have the storage controller being 6 times slower from the response time than it is the physical storage. And because that's the case, if my storage controller is now the dominant response time for the IOs passed from the right to the left, this condition is known as?
It's now controller bound as opposed to being disk bound.
So we're kind of on the picture we're trying to say whack-a-mole. We have whacked them all on the left, which was physical storage. And now the new dominant mole is sitting there in the middle. Anything we can do with that, Ken?
Well, there's a bunch of stuff you could do with the storage controller. You know, you could improve your storage controller's performance somehow. Maybe you change a tuning on your storage controller.
So you make it do work faster.
You could make it do work faster by changing the tuning, right? We want it to go faster. We're just going to say you could just replace your storage controller with a different vendor. Just as the nuclear option here is a way of dropping it. But there's all sorts of different ways that you could make your storage controller faster. The point is less how do you make the storage controller faster, and more that once you do, you now have a new bottleneck. Because now, at least in our picture, our clients are the bottleneck. Not because they're any slower than they were, but because they're now contributing more latency to our overall latency.
And notice how here on the scale went from 0.7 to 0.5.
Right.
So we're increasing the scale, therefore we can see them better, and now the client one is the dominant, so we call this condition client bound.
So Mark, how do I get rid of bottlenecks? I don't want to have a bottleneck. How do I get rid of it?
Well, I think you need to be acknowledging the fact that the bottleneck in this case will exist all the time. There's always going to be one layer that's more dominant than the other. And all you can do is you can address the squeaky wheel a little bit and lower it down by making the other bottleneck more prominent.
Okay. So part of the difference then between 2 different storage solutions might be that one of them, due to the way that it has, what components it has or how it's configured those components, has shifted the bottleneck from one component to another component.
That's correct. So in this case, we have the bottleneck that's moving, and notice how my scale went from 12 milliseconds to 0.5. So what we actually have done here, by applying the principle do work faster, we are doing the work a lot faster now.
Right.
But it's still not perfect, and it will never be perfect, because there's always going to be something that's more dominant. So overall, the solution on the test that we have modified by using SSDs, by using a different vendor, is that we have sped it up dramatically. But yet, if we keep examining, the bottleneck is still going to exist there.
Which is why I have a job, because that's my job, is to find the new bottleneck and to remove it, which is good. Mm-hmm. So, Jay, this would be a good place for quick questions.
Yeah, and I think the conversation is actually really generating a lot of thought. So, obviously, replacing certain components with where the bottlenecks are makes a huge difference if you don't choose the correct one. So we had a question about replacing HDDs with DRAM because we want to do that because it's volatile, and that's absolutely correct.
Yeah.
But one of the questions, I mean, it's just.
Oh, sorry, go ahead.
Oh no, I'm just generating it. It's simply hitting the mole on the head and making it go down doesn't necessarily mean that doesn't have consequences too. So there are two questions that are kind of two sides of the same coin. One is regarding where the solid state drives are in terms of the random reads and random writes. The question is, is there that much of a difference between the performance between random writes and random reads? And secondly, can you identify tools that can help people identify the bottlenecks?
So
let's take the tools question first. So the
tools question.
The tools are typically vendors provide those tools, but they only cover most likely the storage controller, the backend connect, and the drive. So you kind of look at the backend and a little bit on the front end border of the storage controller. The tools for the clients and hosts and the front end connect vary, and people typically use something else. A benchmark that's running on the clients most of the time is the best tool you can have to identify the response time from the client's point of view, which is sort of the missing piece of which you can then derive all the other response time using.
Yeah. We can look at whether we can answer that question more definitively in the blog. There are certain and specific tools we can use. We're trying really, really hard to be vendor neutral as we go through these, because there are some tools I desperately I know of that are mine and not mine, but we'll have to see how much of that details we can put in.
And similarly, we'll answer the question about SSDs writes and reads response times there.
The quick answer to that though is SSDs are they're even faster at reads. But the data that we showed is the average write response time through this big industry survey we did. So yes, they are actually that much faster even for random writes.
Excellent.
All right. Well, let's move on a little bit. Let's move on and see if we can apply the second principle.
So what we've done here, we're going back to our initial slide. Right?
Yes.
This is exactly where we started. It's exactly the same problem that we had before. I want to solve this problem differently because I like doing less work. So instead of making a component faster, I want to solve the problem differently and do less work, and here's my suggestion.
So you're like one of my kids. That picks up less stuff.
Yeah, exactly. So I don't want to make the physical storage faster. I think if it's too slow, let's just not use it.
Okay.
So
if we are not using the physical storage, we're going to achieve that by...
I'm going to suggest we add more cache.
We add more cache.
So I'm going to say if they're slow, let's just not use them. And let's add more cache at the storage controller level.
Interesting.
Now, what would that do? If I do that, then my drives still have a response time of approximately 11 milliseconds in my example. It's just that I don't care because I'm never using them. So my average response time is now the clients plus the front-end connect plus the storage controllers. And what we've done here is this picture is now exactly the same picture we had before when we replaced it with SSDs. It's just that I didn't do it with SSDs. I'm just not using the drive.
So you're doing less work because what's really happening, the drives, the physical storage is doing less work because we just don't address them.
Right. Now,
and that's the concept. It's not the concept that my storage controller is doing less work.
Not necessarily.
It is more that the amount of time we're going to go to this physical storage is different and less, and therefore the overall work there is less. And that's how the principle is applied.
Right. Now, I don't want to leave this picture yet before we talk a little bit more, because we put physical storage in there for a reason. And I'm just kind of saying, well, just don't use it anymore. And that, realistically, you're going to have to go to your physical storage some, right? But if what we can do is we can add more cache, we could change our caching behavior. Almost all storage controllers and even operating systems have ways to control what you cache, like whether you prefer reads or you prefer writes and stuff like that. We could cache more effectively at the storage controller.
But
every I/O I can stop there means I don't have to go to my disk. And so if we can reduce our average latency, this is good.
But we can also address this at the client level. We can change the application a little bit and make the application do less I/O, and that's also going to be applying the principle of doing the less work.
Or we could put a lot more cache in our clients. So something that you and I have both seen, which frustrates us a lot, I think, is going into someone's environment where they're running, quote unquote, a performance test. And what they're really doing is they're doing I/O from their client to their client cache, because they're never actually forcing I/O out of the client cache and off to the storage controller. And
And that's one of the reasons why we call this section hero, is because a lot of times vendors are guilty of generating their hero numbers by hitting a large layer of cache somewhere, as opposed to allowing the I/O to traverse the entire stack.
Which, if you do it on purpose as part of an application, as part of your overall solution design, is fine. If you're doing it to be sneaky, it's not. As part of a performance benchmark. But so again, one of the ways you can solve this problem is just adding cache throughout your layers to avoid using the slow component.
But one of the other things I would like to I'd like to point out is adding the cache is not always because we want to mask out the slow drive, right? It could be sometimes the interconnect that is slower than drive. So in this picture, we can imagine a storage controller that is storing its data somewhere in the cloud, in the web. So they've gone out, and one of these big cloud providers, and we're trying to stay vendor neutral, so I'm not going to name the names, but I'm sure we all know which one I'm talking about. And you can have a tiered storage in there that's all SSDs.
So you've got really fast storage.
Really, really fast storage, but it does take 70 milliseconds to get to it, because you're sitting in New York, and that data center happens to be in San Francisco, I think, according to my fits. So adding some storage, adding cache to the storage controller is going to mask or not have to be using this slow way to get to your fast storage. And it's still an effective way, and it's still an example of doing less work.
It is. And I know we're a little pressed for time, but this is a really good place to point out, when we're saying we're creating a storage solution, your storage solution can span the entire nation, right? So that back end doesn't have to be Fiber Channel or SAS. Your back end could be the Ethernet. Your protocol, you could be doing some sort of object store, right? And you could be going, to a remote object store. Or
it could be RDMA or InfiniBand or anything else you can stretch. However you're going to get
the principles apply for that just as much as they would for a laptop. And we're really focusing here on the principles.
All right, so let's pause a little bit and have a quick second before we go to our third example, MidiBytes per second.
I can tell we're going to have a lot of questions for that one too. So most of these questions are going to be answered fully in the Q&A, but we do need to at least look at them here. So caching obviously is a big question. So the best I/O that we have is the one that we don't have to use. So how do we make the client do less of that I/O?
At a high level, you've got things like, just there are some OS level tunings that most OSs can apply that would cause them to cache differently. If you have more memory physically in your clients, pretty much all of them will cache more if you have more. The problem with caching discussions, and we really struggled with this putting this presentation together, is it gets very, very complicated very, very quickly when you talk about the size of your working set, which is a term we haven't introduced, and you talk about the size of your cache, and you talk about whether it's a read cache or a write cache. So it's a lot more complex than it's easy to deal with here. I think the short answer is, the easiest answer is, in general, more memory equals more cache. And so...
Yeah, and the objective that we had in here, we wanted to make sure that we introduce the concept of cache being important and cache being present everywhere to the audience before we're going to start teaching you how to deal with it, how to recognize when there's cache configured correctly or incorrectly, or whether we should move some of the caching from the client to the storage controller and back. Those are all the concepts that we may be addressing in the future webcasts, especially if the user asking this question can suggest some of the subject that we should be talking about.
Yeah, as we had recommended, as we had thought about earlier, caching and its complexities is probably going to earn its own place in a webinar on its own as a system level or solution level thing. So I think what we'll do is we'll hold off on addressing any more cache questions for this webinar, with the promise that we will address cache in greater detail at a later time, including the Q&A later on. Fair enough?
Fair enough. All right, with that, let's move on. Let's go do our next example of MidiBytes a second. Okay. And this one is a fun one.
So let me set it up, because I want you to answer this.
All right,
I like setting this one up. Okay, so we've got the picture. This is roughly the picture we ended up with on the other two examples, where I've replaced the SSDs, or my spinning media with SSDs. I've got a really nice low latency now with my SSDs. And I'm going to assert that those drives are still a bottleneck, even though they have the least latency of any component that I'm picturing. And my question is, how are they still a bottleneck?
Very, very good question. And the reason why they're still bottleneck is the favorite reason of any storage performance expert, is because latency is not everything. We're also talking about the ability to pass through data, the MidiBytes per second that every component has. So what we have done here is we have flipped the chart a little bit, and now we're displaying different bars in a different color to emphasize it is not latency anymore. This is MidiBytes per second for every single layer. And what you can see in this case is that, first of all, more is now better. So the higher the bar, the better we are in terms of MidiBytes per second. The lower the bar, the worse we are. And we look, and what you've done there is you've done a classic mistake, Ken, where you took a bunch of 7200 drives and replaced them with a single SSD, thinking that SSD is so fast, it can just answer all your problems at once.
Right. So my SSD gave me great latency, but maybe a single SSD, I'm going to make up a number here because I didn't actually go do bandwidth numbers for SSDs. Ooh, I said bandwidth. I try hard not to do that. I didn't get data rate, MidiBytes per second numbers from an SSD. Maybe that one SSD can only do 100 MidiBytes per second. And all my other components can do 300 or 400 MidiBytes per second, even though that I/O has fantastic latency response time. I just can't push enough data.
In other words, it's a common thing called not enough disks. We have to increase the parallelism, if I said it correctly. You have to have enough drives to support all the I/O coming into them. A single drive may not have a pipe thick enough to be able to hold it. So if we add more drives and then look at this entire workload again, this entire solution under test, you'll realize that when those drives are added up together, we can add the MidiBytes per second for all of them, and therefore my whole layer can do more.
So this is the storage vendor's preferred solution to most problems, right?
That's right. A lot of the problems that we have solved in our lifetime. We come in, examine the systems, and say you are not using enough drives. You're hitting one RAID group or you're hitting one drive when you should be hitting a bunch of them, because each one of them carries its own capabilities, and you got to add them up for this particular workload to make things better, to make the performance better. Now, we have another thing in here, and it's called bottleneck moved, Ken. So why did it move, and where did it move to, and what are we looking at here again?
Well, exact same idea that we've talked about before, right? There's always going to be a bottleneck. There will always be some components that can move less data than the rest of the components. So in this picture, we're suggesting that after we've added enough drives, it's now my storage controller that is my limit to how many MidiBytes per second I can move at any given time.
So should we change the storage controller again or add another one in here?
Well, I have to say in this one, we'd probably have to add more storage controllers. So perhaps
increase parallelism. Well, we're not going to go in there.
And so before we change this, this doesn't apply just to MidiBytes per second. It could also apply to ops or IOPS. How many operations per second you're doing at any given point in time. The problem is those are a little more complicated, which I know is going to cause a blog question about why did you say it was more complicated. But I will just assert there are limits to every component about how many operations per second it can do, but those get to be a slightly more complicated question as to how many of those you can do. They don't tend to publish those numbers like they publish MidiByte per second.
That's right. But the real point we're trying to do is we've had two examples based on latency. But you really got to look at the entire world, and the entire world is not just latency.
And it's not just disk drives or storage controllers.
It is not just disk drive storage controllers. The whole thing is pretty round, and you need to be able to balance it. And now on the subject of balancing, here's another example of another bottleneck that is a little bit different than what we've discussed before. And I'm asserting here that we can solve it by increasing parallelism as well. So what are we looking at here, Ken?
So very simply, we've got 4 pipes on our back end. We've got 2 pipes on our front end. If you assume, for the simplicity of argument, that they're the same speed and the storage controller is not doing any kind of massive transformations or caching, then what we're suggesting here is that my client is not going to be able to push enough data through the front end to fully max out the back end. So I'm going to need more pipes somehow. I've got a bottleneck over on the front end in terms of the front end connect.
Very interesting. So if I throw in another client in here with another 2 lines, Now in this theoretical oversimplified example, we have 4 lines coming in, we have 4 lines coming out. We're assuming that they're the same, and therefore this is a balanced, well-designed solution under test.
And we have just a second. I mean, we have a minute. So part of the reason this is here is you and I have both gone into examples where somebody has spent a ton of money to build and then set up a fantastic storage solution from, I would say, the storage controller off back to the physical storage. And then they put one client connected via a single 100 megabit per second line, and they run an I/O test, and they ask, why is this thing so incredibly slow? And I know that that sounds like a silly thing for someone to have spent tens of thousands of dollars and then test it with a single client and complain it was slow. But it happens all the time.
It happens all the time.
And it's because their pipe is slow, or because their client is slow,
or their application has some slowness in there,
or they tested. And so one of the interesting things there, they tested on a public network with a lot of congestion and a lot of packet loss.
Oh, that's a very, very good one. This is when the solution under test is not contained. In that case, your solution under test includes everybody who's causing the congestion, which could be outside of your benchmark, effectively.
Absolutely.
So in the moment you remove that congestion, you've modified your solution under test, but you also may have improved your overall performance because something is no longer affecting those switches anymore.
Right.
Or you have some silly things like mismatch on MTU size or other items like that.
So and I mentioned this because in our very first webcast, our very first, that would be the other one we did. But we pointed out that the part of the goal is to test something as close to your real application as possible. Testing with a single client is fine if that's what you do in your business. But if you're not testing with a single pipe in your business, you should probably be testing with multiple pipes. And if that means multiple clients or multiple applications on your clients or lots of individual connects into your storage controller, if you want to understand how fast it is, that's what you need to be pushing forward in your test environment.
Very good. Which brings us all the way to the closing. We're running very close to the end of our allotted time. So, Jay, you have any questions, or should we move on?
No, I think we're good. I think we should close out.
Okay. So in closing, we're gonna ask the question of which solution under test component matters. We have gone over explaining different examples. We have gone over explaining what each layer is, what the commonality between them. So Ken, which one of them matters? Is it front-end connect? Is it physical storage?
So I want to put an answer that we didn't write, which is it depends. But it depends because it's your slowest component that matters the most. And we'd have to define slowest here by the one that matters to your business, right? So if you care about latency, it's your one that's going to give you the worst response time. If you care about how much data you can push through at a single point in your solution, it's going to be the one that pushes the slowest MidiBytes per second. So it's the slowest subcomponent that matters the most, and that the slowest is defined based on your business.
Very good. Very well put. So to kind of summarize what we have gone over here in the entire presentation, and this is clearly the last important slide, is we went over the layers and the components and which one of them matters most. And we said it's the slowest one matters most, and we define the slowest by introducing a whole set of terminology, being bound by something. It could be a disk bound, it could be client bound. When we identify the bottlenecks and we identify the fact that they always exist, we then can apply the 3 performance principles to alleviate those bottlenecks, so as to shift them, or to change the scale of those bottlenecks to something less significant. And they are do less work, do work faster, or increase power. And with that, we came to the end of our webcast. We'd like to repeat that this was the second webcast of the series. We are planning to have some future webcasts in the future. And you're welcome to download this webcast off of the link provided and follow us on Twitter. And very importantly, we would like you, the audience, to suggest a subject if you feel that what we have planned maybe doesn't align with what you're expecting. Please go ahead and do that. And we're hoping to have the next webcast somewhere in the first quarter of 2016. Jay, I'll turn it over to you.
Yes, as a matter of fact, the PDF and PowerPoint is already available on the website. So you can go ahead and use that link to download the PDF and PowerPoint right now, as a matter of fact. And I would like to reiterate, please, please, please do the ratings. They matter. We do look at them, and they make a huge difference in how we plan and schedule our webinars. So don't forget to click on that ratings button and leave a rating for us on this webinar. And of course,
Jay, I'm gonna make a question or a comment real quick about feedback. Both the written feedback, which I will go through and will read all of the written feedback. Both questions and comments. I'm going to reiterate something though in terms of we'll get to as many of these complex questions coming in through Q&A as possible, and there are some really good questions that I've seen blow by while I'm presenting and glancing at questions.
Agreed.
But I was going to point out something though for people who may have missed the first one, in that the intention of these presentations is to be aimed to give a really good, solid grounding on performance fundamentals and performance topics. And a lot of the questions I see, they're really diving into specifics, which is good. But there's always that constant tension between how do you provide something that people can use as a primer, they can get to their non-performance fundamentals, the performance professional friends that they can use in training. So a lot of what we're aiming at here is to give a foundation for people to build on, which I don't know that we really reiterated that at the beginning of this morning.
Yeah, we're doing a lot of work to simplify the material and to keep this fundamental, foundational theme throughout both webcasts. And sometimes we do want to go deeper, but we intentionally try to keep a little bit shallower to make sure that whenever you are introduced to these concepts anew, you have a better way of assessing and understanding them before diving deep. And with that, I'd like to thank you very much for your time. It was a pleasure to present to you. Ken?
Yeah, these are a lot of fun. So thank you all for attending. Jay, did you have any closing comments that we need to pass on?
Well, only that I wanted to thank all the audience members for taking time out of their day to listen to our webinar. We are striving very hard to try to answer questions that intelligent people may not know the answers to, are smart enough to learn the answers to, and just maybe too afraid to ask. And so we're really grateful that you've taken that time out of your day to share it with us. So on that note, I think that I will go ahead and close the webinar. I want to thank Mark and Ken once more for the really hard work that they've done in these webinars. And brilliant job, guys. Thank you so much.
Thank you, Jay. It's a pleasure working with you.
And to the rest of you, thank you very much. I'm going to end the webcast now, and I hope you have a great day. Take care. Bye-bye.
Take care.